All right, let's do some algebra. It's a little rowdy for a Thursday night, so there might be some background noise, but hopefully not too bad. So anyways, okay, so here we have some actually interesting stuff. So let M1 and M2 be submodules of some R module M. Really, we should say left R module, but whatever. So the M is isomorphic to the direct sum of M1 and M2 if and only if M1 plus M2 equals M and the intersection of M1 and M2 is 0. And this is exactly what we have for vector spaces. So how do we prove this? So by the universal property, we know that there is, and in fact it's a unique R linear map, but all we need is the existence of the linear map. And we go from this direct sum to M, and what we do is we take the ordered pair xy and we send it to x plus y. So the image of this map is clearly going to be all things of the form x plus y, where x is in M1 and y is in M2. So it's precisely this. Then the kernel is, let's see here, the kernel is the intersection. That's because certainly if you have, if you take an element in the intersection, then that the inverse of that element is also in the intersection. Because again, this is an abelian group. So if you have the element and its inverse in the intersection, then you could just take x to be one of the elements and y to be the inverse, and you can do that because these elements, both of these elements are in both M1 and M2, and so it will map to 0. Right, and so what that tells us is that if you have an element in the intersection, then it's in the kernel. Now let's suppose we have an element in the kernel. That means x plus y equals 0. That means x is the additive inverse of y. Let me see here. Where did I should probably keep my marker on me if I'm like filming things. So suppose x plus y is 0. Then x is minus y. So x is in capital M1. Y is in capital M2, but since M2 is a submodule, negative y is also in M2, capital M2. But negative y is x, and so x is in M2. So then x is in the intersection. And similarly, y is in the intersection. So x plus y is in the intersection. And so we have by inclusion there. Okay, so that's why the kernel is this intersection. And now that we know that, it's easy to see that this thing holds, because M1 direct sum with M2 is isomorphic to M if and only if, so this map from the direct sum to M is an isomorphism if and only if the kernel is 0 and the image is if it's an isomorphism if and only if the kernel is 0. No. Right, it's an isomorphism if and only if the kernel is 0 and the image is everything. And the image, we know that the image is going to be M1 plus M2, and the kernel is always going to be M1 intersect M2. So the kernel is 0 and the image is, the kernel is 0 and the image is M if and only if the kernel is M1 intersect M2 and the image is M1 plus M2. So that takes care of the proof of that. All right, let's move on to this thing, because this is a long proof. So a short exact sequence going from 0 through 0 all the way to 0. So again, what does that mean? That means that f is injective, g is surjective, and the image of f is equal to the kernel of g. And of course, these are all module morphisms. So are linear maps. So a short exact sequence is trivial. And what does trivial mean? Trivial means that there exists this thing that this thing holds, that M2 is isomorphic to M1 tensor product direct sum with M3. M2 is this direct sum with this, and then if we put this down here, then this whole diagram commutes, i.e. this box commutes and this box commutes. That's what it means to be a trivial short exact sequence. And again, I think I mentioned this in a previous video, but I think the reason we call this trivial is because you could just take any module M1 and any module M2 and just sort of glue them together to get this short exact sequence. And this short exact sequence is basically the same as this one, except you're using this isomorphism to sort of rename the thing in the middle. But that it doesn't really matter, you're just renaming it. So the structure is really just you took two completely not related at all modules and you just stuck them together. But anyway, so it's trivial if and only if there is a split, i.e. there is or a splitting, whatever. There's a map that goes from M3 to M2 such that S2 composed with G is the identity map on M3. So if you start here, you go through here under S, and then you go back to here under G, and you get the identity. So first, to set this up, these maps down here are always going to be the same thing. So let's take I to be the inclusion map. So we just take an element M1, and we just send it to the ordered pair M1, 0. This, of course, is the 0 in M3. And then projection, this is projection onto M3. So we take M1, M3 and map it to M3. So for the forward direction, suppose that this is a trivial short exact sequence, i.e. suppose that there is a short exact sequence down here, and we have an isomorphism eta that goes from here to here, and suppose that this box commutes and this box commutes. So that's a lot of assumptions. And given those, we want to prove that there exists a splitting S. So for the forward direction, we know that there is an isomorphism eta. So let S be eta composed with J, where J is just like I, except instead of taking inclusion of M1, we're taking the inclusion of M3. So we take J of M3 is just 0, M3, where this 0 is in M1. Then what happens if we do G composed with S? We want to prove that G composed with S is the identity, because that will tell us that this is a splitting. So G composed with S, well, G, because this diagram is, because this diagram commutes, if we're considering this map S goes from here to here. Oh, no. Here we're just using this definition. So S is defined to be eta composed with J. So G composed with S is we just replace this S with eta of J, and we've got G composed with eta, or J composed with eta composed with G, or whichever way it goes. You evaluate at J and then evaluate at eta and then evaluate at G. For composition of functions, it goes from right to left, which is weird, but whatever. So anyways, G of eta, so that's, you start here and then you go through eta and then through G. But since this is a trivial short exact sequence, we know by assumption that this box here commutes, i.e. if we start here and go here through eta and here through G, that's got to be the same as going directly to here through pi, because these two are the same, and that's what it means for this box to commute. So, in other words, we can take this G composed with eta and replace it with pi. So, this map is pi composed with J. So what happens here? So we start at M3, and J will map us to 0, M3, and then pi will map us back to M3. And so therefore this composition here is the identity. And of course that's because of the commutativity of the diagram. All right? Okay, now we have to do the other direction. So for that, define a map eta that goes from this direct sum of M1 and M3 to M2. And what we do is we take M1 comma M3 in this direct sum and we send it to F evaluated at M1 plus S evaluated at M3, which we can because M1 is M1 is in capital M1, which is the domain of F, and M3 is in capital M3, which is the domain of S. Again, for this direction, we're assuming that there is a splitting S, such that this holds. And we want to prove that we have this diagram. So we want to prove that there exists an eta here, such that this map is an isomorphism, and such that this diagram, or this box, and this box, that these both commute. So anyways, so in the lecture notes, after defining eta, he says, just check that this works. And there's actually a lot of work that's left out here. So I think it's really valuable to actually go through all the details here and see why this is the case. Because, and it's not like super trivial, or maybe it is trivial to people who are like really good at algebra, but I don't think it's entirely easy. So it's definitely worth seeing a proof of this. I definitely had to like think about it a little bit and like spend some time and come back to it. So anyways, certainly eta, so eta is you take f of m1 plus s of m3. It's going to be r linear. Why is that a lowercase r? That should be an uppercase. It's r linear because f and s are both r linear by assumption. F is assumed to be r linear and s is assumed to be r linear. Again, that's what it means for these to be module morphisms. Module morphisms are just linear maps. Okay, so this is linear. We need it to be an isomorphism, so we need it to be bijective. And we also need these boxes to commute. So it turns out the boxes are, we can prove that the boxes commute now. So let's do that. For the first one, we want to prove that if we start here and go through here, that's the same as going directly through here. So what happens if we take an element M1 here and send it through I and then through eta? Well, when it goes through I, it's just going to go to M1 comma 0. Then when this goes through eta, it's going to go to f of M1 plus s is 0. But s is an it's an r linear map, so s of 0 is 0. So this is just f of M1. And that's exactly, well, that's exactly what you get if you go through here. If you take M1 and you go through f, you get f of M1. So that does it. So this is this box here commutes. The box consisting of these four thingies. Okay, so what about the second box? The second box, this commutes. So if we start here and go here, we want to prove that that's the same if we go here and then here. So if we go eta of I, that doesn't look right. Oh, I'm looking at the wrong line. G of eta. Okay, there we go. G of eta. So first go through eta, then go through G. Okay, so we take M1 and M1 comma M3 in here. We send it through eta, and that will take us to f of M1 plus s of M3, and we're evaluating this at G. And of course, G is our bilinear, not bilinearity, the single word, but bi space linearity, by space linearity. This is equal to this, because we could just break up the sum. And so here we have G composed with F plus G composed with S. Now what is G composed with F? We are assuming that this is a short exact sequence. So if you start with anything in M1, then after you send it through F, we're going to be in the image of F. but because this is a short exact sequence, that's the kernel of G. So if you send it through G, it's going to become 0. So G composed with f of m1 is 0. How about this? We assume that S is a splitting, and so that means precisely that G composed with S is the identity map. And so when you send M3 through here, all we're going to get left with is M3. But that's exactly what we would get if we would go this way and just take the projection of M1 comma M3. So therefore this thing commutes. What else do we want? The last thing that we need is we need to prove that this thing is bijective. We know that's our linear map, but we need it to be bijective. Okay, and the easiest way to do this is to find an inverse function. And this is actually pretty tricky, and you have to really think about what it means to have a splitting. So if you think about the cosets, like what it means, since G composed with S is the identity, the image of S must contain exactly one element from each coset of the kernel of G in M2. Because basically when you think of the image of M3 under S, you've sort of got a subgroup in M2 which is isomorphic, which is for each element in M3 there's an associated element in M2. And each of those elements must go to they must go back to where they came from M3. So if you had two of them in the same kernel of G coset, then they would map to the same thing under G. And that can't happen because if they map to the same thing, then you must have started with the same thing, because that's the only way for this composition to be the identity map. So I don't know how to write that out in like a more specific way. But it's something to understand. Hopefully just this sentence is enough to convince you of that. But anyway, so after we have that, so suppose we have an element X in M2, then it's in some coset, and so whatever coset it's in has some representative from the image of S3, or the image of M3 under S. So there exists, and it's unique because we have uniqueness. So there exists a unique M3 in capital M3 such that this coset is the same as this coset. I.e., there exists an element Y in the kernel of G such that X is equal to Y plus S of M3. But the kernel of G is equal to the image of F because this is a short exact sequence, and so there must be some M1 in capital M1 such that f of m1 is equal to y. And so then we have x is f of m1 plus s of m3. And so now maybe you see sort of where we're going with this, because this looks exactly like what we had over here. And that's why we're doing this. So, but we want to prove uniqueness of this choice of m1. So if m1 prime would work as well, i.e. if x equals f of m1 prime plus s of m3, then what would happen? You could take those two equations, cancel the x's, cancel the sm3's, and you get that f of m1 minus f of m1 prime is 0, or you get f of m1 is equal to f of m1 prime. But f, because this is a short exact sequence, f is injective. So if f of m1 equals f of m1 prime, then m1 must equal m1 prime, and so we have uniqueness. So for every single x in capital M2, there are unique elements m1 in capital M1 and m3 in capital M3 such that x is f of m1 plus s of m3. Now define psi of x to be m1 and m1 comma m3. So this is a map that goes from m2 to the direct sum of m1 and m3. And this is a well-defined map because m1 and m3 are unique because we proved that they're unique. And clearly, if you look at what happens when you compose psi with phi, so if you take x here, if you take f of m1 plus s of m3 here, then under psi you'll get the ordered pair m1 comma m3, And then if you go through eta, you'll get back f of m1 plus s of m3, which was precisely what you started with. And so this composition is the identity, and the existence of such an inverse proves that eta is bijective, and so this short exact sequence is trivial, and that finishes up the proof.